This lesson, 1.6 on inverse functions, is, I'm not sure if you've learned about it in Algebra 2 yet or not. So the book definitions are really terrible, so I am going to give you the best information that I can about what an inverse function means. But I think the best way to deal with inverse functions is simply to work problems and see how to do inverse functions, and then the definitions will start to make more sense. So I just wanted to show you, if we have a function f of x, then we would show the inverse function as f to the negative 1 of x. So it doesn't mean you're actually doing the negative 1 power or taking the reciprocal, anything like that. It just, that is inverse function notation. And then if two functions are inverses of one another, it means we say that they are 1-to-1. So let's see, a function is 1-to-1 when for a and b in the domain, it says f of a equals f of b implies that a equals b. And again, that is a terrible definition, so we're going to keep going and work some problems and see if we can't improve on that. And if two functions, or if a function is passes the horizontal line test, then that means it is 1-to-1. So every horizontal line has to intersect the function only once. So it's just like the vertical line test. Except these are for horizontal lines, and that is to be able to tell if something is 1-to-1. So for a function f that's defined by a set of ordered pairs to form the inverse function of f, now that's to actually do the inverse function, you would interchange the ordered pairs. So if your function, if you have a bunch of ordered pairs that are x comma y, then your inverse function, all of your ordered pairs would simply be y comma x. No big deal. For a function and its inverse, the domain of f is equal to the range of the inverse, and the range of f is equal to the domain. So honestly, they are just swapped. To verify that two functions are inverses of each other, you want to plug in f, so into the function you want to plug in the inverse, and you will just get x. And then you could plug into the original function into the inverse, and you'll also get x if two functions are inverses of each other. So I know a lot of this has been a little bit confusing, so example 1, you're actually asked to do something. So we want to verify, so f of x is 2x minus 3, g of x is x plus 3 over 2. We want to verify that they're inverses of each other. So we want to do f of g of x, And so let's see what happens when we do that. We're going to take the f function, which is 2x minus 3, and where the x is, we're going to plug in g, and then we're going to work out the algebra. So first I want to cancel my 2, and then I end up with x plus 3 minus 3, and then my 3's will cancel, and I'm just going to end up with x. So guess what? That means, yes, they are inverses of each other. So we want to do a few more examples of that, so let me find my other book, and I will give you a few more examples to help you out. Okay, so this notes guide does not have a specific example on how to find the inverse, so we are going to come up with example 1a, and we're going to say find the inverse of f of x equals 4x. So that's a pretty simple one, and in order to find the inverse, what I like to do is instead of f of x, I like to think of this in terms of y equals 4x, switch x and y, and then solve back for y again. So we get y equals x over 4. So after we did that, we switch x and y and solve back for y. That is the inverse, x over 4. So in order to find out or to prove that they're inverses of each other, you do f of the inverse of x. So let's see, I'm off the page a little bit here. And so you plug in this inverse, x over 4, into the original function. So we do 4 times x over 4, and we see that our x's cancel out, leaving us with just plain old x. So that's the rule to know for sure if they're inverses. When you plug one back into the original, you get the identity, or just x. So the key to that was, how did you find the inverse, Miss Sarfy? You replaced f of x with y, and then you swapped x and y with each other, and so that kind of goes back over here to interchange the ordered pairs. Then you solve back for y again. Okay, so now I'd like to do another example like the original example 1, and I'm going to use my extra piece of notebook paper for that, and I've got some algebra on there, so let me tear this off. And so the problem is, and I'm going to call this example 1b. Let's see, am I on the page? Example 1b, I want you to first find the inverse of f of x equals 4x minus 1. Then verify that the function and its inverse are equal to the identity. So in order to first find the inverse, I'm going to think about this as y equals 4x minus 1. Then I'm going to swap x and y. So x equals 4y minus 1. Then I'm going to solve for y. Plus 1. So x plus 1 equals 4y. Divide 4. Divide 4. Y equals x plus 1 over 4. So that is our inverse. Sorry. You can pause it and look back at my work if you need to. So this is the inverse. Now, to prove that they are inverses of each other, or to check ourselves, I guess, we're going to do f of negative 1 of x. That means we're going to plug in what we found for the inverse into the original formula. So the original formula is 4x minus 1. So we're going to do 4 times x plus 1 over 4 minus 1. So these guys cancel, x plus 1 minus 1. And we just get x, which is the identity. So we did it. Okay, so now we want to talk about the graphs of inverse functions. If the point a comma b lies on the graph of x, then the point b comma a lies on the graph of the inverse of x, and vice versa. The graph of the inverse of x is a reflection of the graph of x in the line y equals x. So if you've got a graph of your function, so here's my function with a squiggle, then the line y equals x goes like this. So then your inverse, you're going to take each point and it'll be right on the other side of that line. So, okay, that's a terrible drawing, but you get what I'm saying, that each point, the reflection is across this line, y equals x. So on the next page, we get to talk a little bit more about one-to-one functions and whether or not the inverse exists. So if a function is one-to-one, that means, and we want to go with kind of a formal book definition here, if a function is one-to-one, that means for a and b in its domain, f of a equals f of b if f of a for a and b in its domain, f of a equals f of b implies that a equals b. Function has an inverse f of -1 or f to the -1 if and only if it is one-to-one. And to tell whether a function is one-to-one from its graph, we're going to use the horizontal line test. So let's take a look at example 2. We're looking at this graph here. Does it have an inverse? So we just got through saying that for something to have an inverse, it has to be a one-to-one function, which means it has to pass the horizontal line test. So if we look at this spot right here, we see that our horizontal line actually crosses that graph in 3 places. So we could say no, it does not have an inverse, and the reason why is that it fails the vertical line test. Okay, so for this next section, we're going to go through the steps, which I've already shown you one time, of how to find inverse functions algebraically. Now, whenever you're working something out in this pre-calculus class, if there is something you don't know how to do, I want you to turn back into the section of the book. I'm going to put that under my camera here. And I want you to look for one of these blue boxes. And it's got highlights and everything, and the blue box generally will have instructions for anything that you need to know how to do all throughout the rest of the semester. So I'm simply going to take these instructions from this blue box and write them down into the notes, and then we're going to do some examples where we actually use them to solve problems. So it's not a good idea just to write down a list and go, oh yeah, I think I'll remember that when test time comes. No, you have to write it down, learn the steps, and practice. So step 1 is to use the horizontal line test. To determine whether f has an inverse function. And then replace f of x by y. They use some bigger words. I'm just going to say switch x and y, solve for y, replace y by the inverse of x, or f to the negative 1 of x in the new equation. And then verify that they're inverse functions of each other. And remember how we did that. We plugged in the inverse of x into the inverse of f into f, and we saw that it equaled x. And then you can also take the inverse function and plug the original f of x into that. Either way, you'll get x both times. So let's find the inverse of f of x equals 4x minus 5. And so one thing, it's good to know about your parent functions from the last one of the last few sections, okay? So if you can look at this thing and say, oh yeah, 4x minus 5, x is to the first power, this is like y equals 4x minus 5. This is a linear function. Okay, it has a slope of 4, a y-intercept of negative 5. It not only is it a linear function, but if I can visualize it, and if I do the horizontal line test, it'll pass. So now I'm going to follow my steps. I'm going to replace f of x by y, and then I'm going to switch them. X equals 4y minus 5. Then I'm going to do the algebra to get y by itself. So I'm going to add 5 to both sides. So I get 5 plus x equals 4y minus 5 plus 5 is just 0. So I'll divide that by 4 on both sides, and we get y equals 5 plus x over 4. And so that's a good example. And then we want to take what we got for the inverse, plug it back into the original. So we're supposed to replace the y with f to the negative 1 of x. So let me take this that I have circled and plug it back into the original. So f of x equals 4 times 5 plus x over 4 minus 5. So when the 4's go away, then we can see that we have 5 plus x minus 5. We're just going to get x, which means that that is the inverse. So we'll do some more of these problems in class, but otherwise these notes are finished.